nanoHUB.org.
Online simulation and more for nanotechnology.
All right, folks, these three concluding lectures could be viewed as kind of overview of what we covered, even though I'm not going to repeat things. But I would basically emphasize the conclusions from somewhat different perspective. But anyway, so we will focus on why this important recent development in the field, in the science of light, namely plasmonics and metamaterials, which enable unparalleled control over light, play such an important role in nanophotonics. So, and outline for these three lectures is here. Why actually nanophotonics? The role of silicon nanophotonics, which is basically nowadays technology, or let's say the near future technology, and what do we expect from metamaterials and plasmonics, why we think it's basically next step in this direction to process information faster. And also, again, I emphasize the importance of material platforms and fabrication approaches. I should acknowledge contribution from a number of my colleagues here in Purdue and outside who helped with preparing this material, covering most recent advances in related areas. So we could, well, as I pointed out, of course, electronics is an exceptionally mature technology with really fantastic capabilities. And in that regard, of course, it was comparing nanophotonics against electronics. I mean, in a very general way, you could say with electronics, the units of information are electrons, whereas with photons are photons. And to pass this information in electronics, we use wires, whereas in photonics, we use all type of waveguides, from optical fibers to silicon waveguides. And the fundamental difference why there is so keen interest in photonics, it's that with electronics, you are limited by some fundamental delays, such as RC delays. Remember this aspect ratio consideration. And as a result, the frequency which you could go up to with electronics is around 10 to the 10, at best 10 to the 11 hertz. So in other words, you could translate it in number of operations per second. With photonics, you're limited only by the carrier frequency. And I want to discuss quantum photonics, which I already which I already covered to some extent, overviewed at least. With quantum photonics, you're actually not limited even by the carrier frequency. In that case, because you could take advantage of this quantum speed up, of this unique quantum superposition, in principle, you could process larger volumes of information. And in that regard, you actually the way it looks now, you're limited by your ability to control this quantum superposition. But that's something what we overviewed recently. So within these three concluding lectures, I focus on kind of classical nanophotonics and electronics. Well, when we're speaking of nanophotonics, of course, we should start with fiber optics, and we should remember that that's the solution in terms of sending information over large distances, over C distances, and that's really remarkable progress. And in that regard, whatever we're trying to develop should be comparable with what fiber optics actually delivers. And so with optics or waveguide, we basically transmit information, which is packaged in photons. When we speak of integrated optics or nanophotonic circuitry, we are talking about processing information, how you basically do all these logic operations, switching, rerouting. So that's what we mean by integrated photonics or this nanophotonic circuitry, which is basically the same thing. And we will discuss again these new paradigms, new approaches, plasmonics and metamaterials, which are closely interrelated. And the key thing behind this is that you could bring light down to a nanoscale by using plasmonics and various ideas from metamaterials. Whereas with silicon nanophotonics, you're still diffraction limited. And smaller footprint, in principle, allows faster and more complex processing of information. You could place by far more elements on the chip. So going small, of course, making a big difference. And again, let me mention, yet another step is going quantum. So when you really bring it to exceptionally small volumes, then quantum phenomena become important. And that brings yet additional advantages in terms of processing information based on this entanglement phenomenon. So this slide illustrates in a somewhat different way, which we already pointed out. It's historically we describe the speed with which different technologies processed information, starting from telegraph, when you basically have roughly 1 bit per second, going to telephone, about 1 kilohertz speed, or 1 kilobit, 1 kilobit per second, so transcontinental cable, coaxial circuits. And here's our favorite CMOS electronics. So that's the leading technology of nowadays. Although the role of nanophotonics become progressively larger and larger, it's like, if you would like to compare, it's like with this green energy. I mean, we're still around coal and oil, but the role of all this type of green energy, solar energy, basically exponentially increases and eventually is going to win. So with CMOS electronics, it's wonderful in terms of the special scale, because the size of elements out of which you build nanoelectronic circuits, it's basically going down to very few nanometers, like size of the transistors is around 4 nanometers, but you're still limited in terms of the frequency. Remember, we considered all these things like RC delay, energy, this aspect ratio, and basically it's around 10 to the 10, at best 10 to the 11 operations per second of hertz. So with photonics, you're limited only by the carrier frequency. So basically you could go way above 1 terahertz, up to 10 to the 15 in principle. But the sizes are relatively large because typical optical elements such as optical fibers are microns or several microns. So the idea of Plasmonics and Metamaterials is take advantage of both worlds, so the speed of electronics and the size of photonics, and merge the two. That's actually the biggest attractive part about Plasmonics and Metamaterials. So I should say that quite often people say nanophotonics, speaking of, for example, silicon nanophotonics, which is not exactly true, as I said, because nanophotonics implies actually going below 100 nanometers. And with conventional dielectric structures, you cannot do it. So you have to use these plasmonic structures or metamaterial approaches. Some a little bit basic information about the way we compute, what are the challenges, because by showing all this, I'd like to emphasize the importance that new technology should start from whatever already is available. So it's not enough to have idea, no matter how brilliant it is. You have to know how the technology looks now, what are the constraints, and what are the accomplishments. Quite often we're not that familiar with this, and it could hurt the potential impact of your discoveries. So therefore, I decided to put the several slides outlining basically how computers look like and what are scales, what are the speeds, what are the costs involved, so that we would know what we are competing with. Because clearly this, nowadays computers are a very powerful thing. First of all, what kind of scales are involved? Of course, we have this chip, okay, chips. And on one board, you have a number of chips. And typical separation between chips is millimeters. So you also have these interboard separations, which typically involve sizes like centimeters, and intershelf, because on shelf you have several boards, on boards you have several chips. When you speak of intershelf distances, it's basically something like tens of centimeters or close to a meter. When you talk about different network elements, so of course that interact basically separation, that involves distance like meters. And if you talk about intersite, then it involves distances like kilometers. And finally, when you compare distance between some central office and network elements, it's actually, we are talking about 10 to 1,000 kilometers. So that's kind of how this computer network looks like. And here I'd like to show this slide that it's actually amazing how visionary prediction some people do. And this one comes down to 1989. And that's actually outlines like the roadmap for silicon nanophotonics. And amazingly, as I will show with following slides, the way it develops now, it's very much similar to what was suggested in 1989. Of course, it has these optical fibers where you bring information from the outside world and optical fibers to return it to the outside world after processing information on a chip. It involves all these modulators, which is the key thing. You need to switch. You need to do some logics. All this photodiode, basically in this case laser diode, coupler, and amplifier. All these many elements which you have in nowadays understanding and of the roadmap of nanophotonics. So the whole idea, this deep scaling of optics, which uses materials with high refractive index, silicon, and silicon does have high refractive index. But again, it's still diffraction limited. And of course, from the very beginning, it was understood that materials you're going to use for nanophotonics should be compatible with CMOS processing, which is used now for nanoelectronics. So this is how it looks like the modern way for nanophotonic circuitry, which is pretty much similar to what is outlined in this in 1999. And so basically you bring line through optical fiber. You bring information through the optical fiber. You couple it to a chip. So then you, by using this wavelength division multiplexer, you send information at different wavelengths into different channels. You process this information by using this optical cross-connect, and the operation of this controlled by nearby locating very large scale integrated circuits, VLSI. And the whole operations, of course, you have delay lines for signals going in different wavelengths, so you should control delay. And the whole operation is controlled with photodetector. After you process all the information, you send it through optical fiber back to the outside world. So the point here that's pretty much the roadmap, very much similar to what was suggested long ago in 1989. So let's look at some numbers related to where the computing nowadays. Why am I speaking of computing? Because as I said, even though it's not the only application for plasmonics and metamaterials, one of the biggest motivation is nanophotonic circuitry to process information faster. Having this said, still there are many other applications, sensors, energy, data processing, many other, data recording, but still this faster processing information remains in the heart of driving forces behind nanophotonics. So what it shows, it's like how the power of supercomputers developed with time. So, and if, let's say, in the past, people did this, like, let's say, in 94, it's 100 giga floating operations per second, flops. So then nowadays, we are talking about 10 petaflops, which is, peta is 10 to the 15, and 100 means it 10 to the 17 floating operations per second. So it develops pretty much fast. So, and that development largely was possible because of scaling down, basically by employing this Moore's law, making things smaller and smaller and placing more and more elements. But the reality is with electronics, there is indeed no saturation. You cannot go even to smaller sizes. So because we already facing the sizes at which all these quantum phenomena become important anyway. And again, coming back to a little bit to history, like this is how it looked supercomputer in 2006, and it's huge. I mean, look at this. This is a human, and it's just one big supercomputer, and that was able to process roughly 10 to the 14 flops. So, and the same type of processing in 2011, 5 years later, that the whole thing, it's just like, in terms of scaling sizes down, it's truly dramatic development. By the way, there is a number of slides with credit to Yuri Vlasov, a good friend of mine, who was pretty much a driving force, a leading expert in developing nanophotonics back at IBM. And only last year he moved to Urbana-Champaign University, but for, I believe, like 15 years or so, he was pretty much a leading researcher in this effort to develop nanophotonics for computers in IBM. So he is the expert in this area. In my opinion, the best one. So in terms of all these fiber cables, that's the way it looked in 2006. It's actually remarkable. It's unbelievable how many all these cables you have. And in 2011, which is already deep in the past, so basically 100 times more fibers. We are talking here almost like 500,000 fibers. It's pretty much located in compact fashion. So this table summarizes how actually these things develop in terms of speed and cost. And when it comes down to real-life applications, that's something you really have to take into account. Well, let's say, first of all, in terms of peak performance. Roughly, you could say that every 4 years, the speed in terms of these flops increases by a factor of 10. You see, one PF petaflops, 100,000 petaflops. So roughly 10-fold increase every 4 years. In terms of number of optical channels, so you could say that roughly, again, factor of 10 every 4 years. Here it's 48,000, well, I could say roughly 10 to the 5, here's 10 to the 6, 10 to the 7, 10 to the 8. So, and in parallel, in terms of speed, you could this 5, 10, 20, roughly 25. So the speed keeps increases in terms of gigabit per second. So the other very important thing, actually, that becomes like one of the key things about computers. It's power consumption. It's just unbelievable how much power consume our computers, and that becomes a very serious problem. So again, if you look what's happening in 2008, it's 50 milliwatt per gigabit per second. And if you translate it, because this is power times time, and power times time gives energy. So it's roughly 50 picojoule per bit. And then you have like 25 in 2012, 50 milliwatt per gigabit per second. And it's projected in 2020. Although, frankly, I think that by that time, you might have a very different disruptive technology. So that's all based on projection with existing technology. But in my opinion, the time came to have disruptive development involving probably both some elements of plasmonics, metamaterials, and quantum. But anyway, so the goal now, like there are these grants like a University Research Initiative, MURIS, which aim to developing 1 femtojoule per bit. That's what the goal now, 1 femtojoule. Its femto is 10 to the minus 15 joules. So basically 1 photon per bit. That's what we are talking about now. That's the goal now. But that's almost for sure would have to involve quantum ideas. So basically, it's already what we are now aiming at. It's already beats this table, which kind of based on the existing technology. And the optical cost-wise, which is also a very important factor. So in 2008, it was 10,000 per terabit per second information. So, and then it drops down quite dramatically, roughly by factor of 10 every 4 years. So in 2016, it's $170 per terabit per second. So no matter, well, the reason I'm bringing this up, I mean, it would look really naive if it would come with new idea for new technology. And if you talk to serious people who, like VCs, venture capitalists, who might be considering to invest in this, they would say, hey, well, nowadays it's, let's say, that much. How much your technology would cost? So it's not enough just think only in terms of physics behind your technology, but you also have to look into all this consideration. How your technology is compared against the existing one. So then it could be seriously taken. So that's the thing to keep in mind. So there are different visions how nanophotonics could be combined with nanoelectronics. And one of the quite common approaches is basically have this nanophotonic circuitry atop of all this nanoelectronic circuitry, so that all the functionality would be done largely by nanoelectronics, which of course is very powerful in terms of switching and so on, whereas the sending information would go through all optical routing. It's just like one of the roadmaps for this off-chip nanophotonics interconnect. So it's basically, you see the idea, it's off electronic chip. So whereas memory layer and processor layer, largely based on electronics, would be underneath of this nanophotonic chip. So that's some kind of map of the road coming from leading, like in this case, IBM. And you could see that everywhere it's Yuri Vladimir, who is, as I said, has been a key player in this field. So that's how it looked in 2015, all these optics units, memory units, processor, and this is like how they projected it would look in 2020. So it's like kind of three-dimensional structures. You could see here this processor actually atop of this memory, and underneath you have these objects. So you kind of basically separate these different chips. They are largely optical photonic chips and electronic ones. So that's again the press releases coming from IBM in 2000. It's 2012, so some time ago already. But there's several things to point out here. There are already a number of photonic components, including germanium photodetector, including wavelength division multiplexer, also photonic, including modulator. It's all actually optical components. It's also kind of three-dimensional. It tried to take advantage of the third dimension. And you could see here that there is nearby optical interconnects along with electronic interconnects. So clearly that as much as possible, people trying to use nanophotonic components, basically because with nanophotonics you could send information faster. But still, in terms of processing information, I would say electronics still plays quite an important role. So this is somewhat later release coming from 2015. It's also courtesy of Yuri Vladimir, who gave this slide to me. Of course, now you could find it on the web. So it shows the cassette carrying several hundred chips intended for 100 gigabit per second transceiver. So that's the way it looks like, and that's basically the roadmap for IBM. So that brings us back to Plasmonics, because with silicon, yes, there is a roadmap, there is still room for development, but as I said, the limiting thing is that your diffraction limited. You cannot, with nanophotonic circuit, you cannot go below this lambda over 2m in terms of handling light. And this is just a reminder that what kind of plasmonics makes a difference. It's basically confinement of electromagnetic energy. When you excite this surface plasmon, and when you use metals where basically electrons are free to move, like if you have electrical field applied, then electrons would move. You would have excess electrons from one side and lack of electrons from the other side. That would mean that electrons would bounce up and back because there is clearly restoring force here, and the resonant frequency for this oscillations would depend on the shape and size of the structure. And that's the nature of surface plasmon resonance. The particle could be much smaller than the wavelengths. The other quite often used structure is basically two metallic structures and dielectric gap in between. In this energy, it tends to be concentrated mainly between these two metallic particles, and the size of the gap could be as small as 5 nanometers. So this is an example of what we call local surface plasmon resonance, and that acts pretty much like nano-antennas, with the concentration, with confinement energy down to very small volumes, below 10 nanometer in size. So that's the important advantage of plasmonic. And another version of this plasmonic excitation, it's propagating surface plasmon waves, which you call surface plasmon polaritrons. And I already showed the slide. In this case, for example, you have this metal insulator, metal waveguide, and light comes from outside world, for example, through optical fiber. This is the wavelengths. And within this structure, the wavelength dramatically shrinks. Remember, for surface plasmon polaritron, although the frequency is optical, the wavelengths could be much smaller than the wavelengths of light in free space, going down to, let's say, 10 nanometers. And as I already mentioned, Ilya Blanovic called them X-ray at optical frequencies. And that's the idea behind this confinement. So not only the wavelengths become smaller, but also in the vertical direction, the confinement of this wave becomes much smaller. And SPP could be used as interconnect, basically sending information along the chip. Since losses are more or less significant here, you don't want to use it to send it for large distances. But when you're talking about microns, that's very realistic. And on a chip, that's the scales you have. You don't have to send information for really large distances. So this is like local confinement. You could use it for nanoscale laser, for plasmonic switch, or antenna. But if you send it, you use these surface plasmon polaritrons. And for, let's say, tens of microns, even 100 microns, that's a feasible way to send information which carried by these surface plasmon polaritrons. And that's actually the vision. At some point, we developed it, discussing with Yuri Vlasov. It's pretty much what we saw for this photonic circuitry, but the difference, we incorporated a number of plasmonic elements. So with the idea that to increase the confinement, to decrease the footprint of structures you use. Otherwise, it's pretty much the same nanophotonic circuitry roadmap. So in this case, you have, again, optical fiber, but the size of electromagnetic wave in optical fiber is very large. I mean, it's, let's say, 10 micron or so. And we would like to confine it to a smaller scale. For that, you could use the small couplers, like small particles or whatever, so that the electromagnetic wave in a fiber would excite the surface plasmon excitation, and you would bring it to this chip. So fiber coupler combined with Plasmonics coupler. By doing so, you actually squeeze the size of the volume of electromagnetic excitation. So then again, you send it to wavelength division multiplexer, which sends different wavelengths into different channels. So you would have to use these nanoplasmonic delay lines. For that, you could use this kind of hybrid technology. Remember, I told you that with a photonic crystal, when you have a defect, it acts as a waveguide. This is basically photonic waveguide. But to introduce this delay, you could use these plasmonic structures. Because of coupling to these plasmonic structures, the group velocity would be slowed down, and that could be used as a delay line. And please note, this is kind of hybrid technology. That's actually a while ago we thought with Yuri how we could actually do it. So, and again, it's combined this nanophotonic waveguide based on photonic crystals with plasmonic structures. It's for optical cross-connect, where you basically do switching. You could use this Max Zender's interferometer based structure, but it could be based on a photonic crystal, and also could be controlled by plasmonic structure, which enables a stronger confinement. In terms of photodetector, which controls the operation of the whole structure, so we could use again this hybrid approach. Remember, I mentioned it in previously, when you have a cavity, again, in a photonic crystal, you have a defect, and in this defect, you have a cavity mode, which is diffraction limited, but quality factor could be enormously large. And again, the confinement here, because of this multiple Bragg scattering, basically, because of the periodicity. Light cannot propagate inside of the photonic crystals, but it can exist here. So the quality factor could be easily a million and higher. But to accomplish even further confinement, you could place a plasmonic antenna inside of this photonic cavity. So you basically combine, you have this hybrid technology. First, you create this photonic cavity by making a defect in the cavity. In quality factor could go up to actually hundreds of millions, but volume still is limited by the wavelengths. And then you add plasmonic antenna where volume could be exceptionally small, let's say 5 nanometer cube, for example. And that would enable very strong confinement. So you could also use these photonic crystal bands. Remember the advantage of this waveguide based on photonic crystals, you don't have losses when you bend your waveguide. Normally, any waveguide, when you bend, you have losses. And you could use this plasmonic splitter. And basically, the idea, it's pretty much like this nanophotonic circuitry suggested for silicon, but here you introduce plasmonic structures to further increase confinement of light. So we called it Plasmonics Enhanced Microphotonic chip. And the truth is, I think I still believe that future technology would be somewhat like this, would use these elements, because it really have very high speed and much stronger confinement. So, and the advantage is it's a hybrid technology. It takes advantage of something which already well developed with further new ideas, like in the case of this, in this case, plasmonics, which could provide this strong confinement. This is a little bit more recent that we worked out with Yuri Vlasov. This recent Muri project done with Stanford, and Purdue was a part of this. So, and Mark Brangersma, my good friend and colleague, actually developed this kind of visionary slide. And again, so it's has all this plasmonic and dielectric structure. First of all, it's called hybrid circuits. I mean, the idea is very straightforward, because same metallic structures could be used for electronics, because metals conduct electrical signal, of course, and for plasmonics. So that's why we call it hybrid structures. And this is, of course, a big advantage. So it has a number of nanosources, which could use all type of plasmonic structures, nanosources of waves, light, basically, but it could be in the form of plasmonic waves. A very important part is modulators. And for modulators, we could use this dielectric plasmonic waveguide interface of different types, and there could be actually different suggestions. We see what you could see here, this plasmonic modulator, which basically is plasmon wave, which is controlled by electrical signal. So Harriet Water from Caltech, who also a part of this project, call it plasmonstra. So basically like transistor, but in this case you control the plasmonic wave with electrical signal. So that would play the role of modulators. Very much similar to what we consider for nanophotonic circuitry when we are talking optical cross-connect. Of course, multiplexers, which could also involve photonic crystal cavity and some plasmonic structures, and in the end, photodetectors. So, which could also, these photodetectors could have some like gap, like basically some plasmonic structures, like in this case, a thin film silicon photodetector, which combined with gap nanometallic slot guide. So it's a hybrid structure, and generally speaking, we don't need to go into details, is that every time when you could take advantage of stronger confinement enabled by plasmonics, you place it on otherwise nanophotonic circuitry, and electronic circuitry. That's the hybrid approach. In this case, you actually have hybridization, if I may say so, of three different technology. Electronic circuitry, like for example, the switch you control with electrical signal. Nanophotonic circuitry based on silicon. You see there is a number of like these silicon structures. And plasmonic technology. So plasmonic with largest confinement of electromagnetic energy, silicon, where losses are very small, but you're still limited by the diffraction limit in terms of sizes, and electronics, which is of course a very mature technology and allows all type of switching. So this you hybridize here 3 different technology to take advantage of each of them. So I guess I'll stop here, and that we'll continue on Friday from this slide. And we will look at many different applications of plasmonics going beyond only nanophotonic circuitry. The goal of today's consideration was to show how the nowadays technology work, what is the roadmap for current technology, and to see whether plasmonics and metamaterials could bring some kind of disruptive ideas into this technology.